an example on capacitance and dielectrics, which was the topic that we finished last week. And then we're going to finish today's chapter 16 by introducing capacitors in circuits, series and parallel. Okay, so I wrote some of the equations that we went over last class, the equation for a capacitance and the equation or the relationship between the capacitance when you introduce the dielectric. So remember that the K value in this situation is the dielectric constant. It's not Coulomb's constant, okay? Now the two additional equations are this: the dielectric strength and the voltage when you introduce a capacitor. Sorry, the dielectric. When you introduce a dielectric, the electric field and the voltage, they are lower, right? They are reduced. We call the electric field when there's a dielectric, right? So when there's a dielectric, like in here, we say that there is a dielectric strength. And it's a vector as well. And we label it with capital D. That's the dielectric strength. It has the same units as electric field because it's just affected by the dielectric, by that equation there. In this example, they give you the dielectric constant. Again, no units. They give you the dielectric strength. You are given the capacitance. That's the capacitance you need. So this is the needed capacitance. And you have the voltage between the plates of 4 kilovolts. They want you to find the area between the plates. Okay, so if they tell you that that's the capacitance that you need, that means that that's a capacitance without dielectric. But the dielectric strength is this. So how do I use this to find the area? Well, even though you have a dielectric, the capacitance, this still holds. So you basically use this equation, right? The area is what you want. The distance you don't have. The capacitance is this. So, and E naught is a constant. You need to find the distance between the plates. You need to find this. To find the distance, you are going to use the voltage and the electric field. And you have the electric field because you have the electric strength. The dielectric strength, the dielectric strength is the electric field divided by the dielectric constant. So I have the dielectric strength. I want the electric field, and I have this K. And that's how you find the electric field, by using that relationship. So let's see here. The electric field, if you do the math here, is 8.0 times 10 to the 8 volts per meter. So that's the electric field. If I have the electric field, I can use it to find the distance between the plates by using the electric potential relationship, right? Basically, for a capacitor, V equals to E T. Okay? So if I use that equation, right? The voltage is 4 kilovolts. That's 4,000 volts. Or 4 times 10 to the power of 3 volts. That's 8 times 10 to the 8 times the distance. Now, if I do the math here, distance is 0.5 times 10 to the negative 5, should be 0.50, right? Yes. Times 10 to the negative 5 meters. That's the distance between the plates. So I have the distance. Now I can use that to find the area because I have the capacitance. So 0.10 microfarads, which is that 0.10 to the negative 6 is E naught, and E naught is your constant, right? It is your 8.85 times 10 to the negative 12. That is your E naught. Area multiplied by area over the distance, which is 0.50 times 10 to the negative 5 meters. Okay, so well, let's see also the math here. Area equals to 0.10 times 10 to the negative 6 multiplied by 0.50 times 10 to the negative 5 divided by 8.85 times 10 to the negative 12. All of those powers of 10 will give me 10. 0.10 times 0.5 is 0.05. 0.05 divided by 8.85. .005,649 multiplied by 10, I get 0.056. So 0.056 meters squared. And that's the area between the plates. Let's suppose they want it, so let's do the exercise. Convert to centimeters squared. Convert to centimeters squared. Let's suppose that you were being asked to do a conversion like that, right? If you were being asked to convert it, you have to multiply by 100 twice, basically by 10,000. So you move the 0, you move the dot, 1, 2, 3, 4. So that will give you 560 centimeters squared. And that's another example where we use the capacitance equation and the dielectric. All right. Remember, I said last class that the dielectric changes the polarization of atoms inside a capacitor because you are introducing an insulating material, which allows you to increase the capacitance of the capacitor without producing a short circuit by reducing the distance to match. Okay. All right. Any questions about this? All right, so you already took quiz number 1, and assignments 1 through 4 or 5 are due next week. So you should be working on assignment 2 and 3 in preparations for Thursday quiz, right? So make sure you're working on that today after class. And right now I'm going to finish chapter 16 by introducing circuits with capacitors. So make sure that if something is not clear, then you can ask questions, because we're gonna probably introduce current at the end of today, and tomorrow in person, we will introduce circuits with resistors, which is almost the last topic before the first exam, okay? All right, so let's erase the whiteboard right now, and let's go into circuits with capacitors. All right, yeah, let's just do it on the whiteboard for now. Okay, so one of the last topics or applications, sorry, for capacitors is to use them in electronics. I did provide a brief explanation of how we do that last class. So now let's see what we mean when we talk about capacitors in series and in parallel. All right, so these will be capacitors in series and parallel. So for capacitors in series and in parallel, the idea will be to find a way to combine them into one, and then use that combination to explore the charge, the capacitance, and so on. So what is the first step on this? When we have them in series, or for capacitors in series, normally the way they look is like this. You have a wire, capacitor here, more wire, capacitor here, more wire, capacitor here, and they are all connected to a power supply or a battery. So that's your very basic circuit. This is the voltage supplied by the battery, and this will be C1, C2, and C3. The way you can explore this is by understanding that when you have a circuit, and you're going to explore this tomorrow in the lab, is that in a circuit like this, we have current. Now, it doesn't make sense to talk about current if you have capacitors. So then we talk about charge, because capacitance is charge divided by voltage or potential. So technically, you have charge flowing through here. And because they are in series, all the charge is the same. So you write here that the charge on 1 equals to the charge on 2 equals to the charge on 3 equals to the total charge. So the total charge on the circuit is the same on each capacitor. So what happens with the voltage, however? By conservation of energy, the voltage on 1 plus the voltage on 2 plus the voltage on 3 is the overall voltage supply. So the voltage is split among each capacitor. Okay, but we have this equation, right? Voltage is Q divided by C. So for each capacitor, since they all have the same charge, V1 is Q over C1, V2 is Q over C2, V3 is Q over C3. And what's V? Q over C equivalent. We call that the equivalent capacitance. Well, all the charge is cancelled and we get the equation to combine capacitors in series, which is basically 1 over C1 plus 1 over C2 plus 1 over C3. That's equal to 1 over C. And remember, Q is constant. Not voltage, but charge. That's capacitor in series. All right. Now, what about parallel? For parallel, the geometry is a bit different, but we're still going to use that equation. So for parallel capacitors, the way they look is like this. So let's write here parallel. And by the way, we still use the equation C equals to Q over delta V. Okay, capacitors in parallel look like this. Capacitor 1, capacitor 2, and capacitor 3. And they are all connected to a battery like that. That's your V, C1, C2, C3. What we notice is that these two ends, right? There is nothing in between here. So all of these capacitors are at the same potential, meaning that C1, C2, and C3, they all have the same potential or voltage as the one provided by the power supply or battery. So V1 equals to V2 equals to V free. You see that? And it's equal to V. The V of the power supply. Now, what's V though? V is Q over C. Now, the charge in this case is not constant. So you say Q1 over C1 plus, sorry. The charge is not constant, so Q1 plus Q2 plus Q3 is the overall charge of the circuit. Is the total charge. But what's Q1 though? Q is C times V. Now, C is different, but V is the same. So we can write C1 V1, C2 V2, C3 V3. That's your C equivalent times V. Now, because of this, V1, V2, V3, and V. And you get the equation for like this, but now for parallel, for parallel capacitors. So C1 plus C2 plus C3, that's equal to C equivalent. And these are the equations for series and parallel capacitors.
Professor, could you move the camera a little bit more to the right? Thank you.
Means the same. Now we're going to use those equations in circuits. All right. Now remember, this is for capacitors. If you have seen this with resistors, please keep in mind that they are similar but not the same. Tomorrow we're going to do resistors in series and parallel, and the equations are sort of reversed because of the conditions, right? A resistor is different than a capacitor. So please, when you are doing the problems, make sure that you know whether you are working with capacitors, which we're going to do now, and tomorrow when we start working with resistors. All right? Okay. So let's do some problems. And the idea behind circuits is a variety of circuits you can be given in a certain situation. Meaning you have to figure it out whether capacitors are in series, in parallel, and which equation to be used. So let's do some exercises, all right? Yeah, start with one that is very common, and then we can move from there. Okay. Example on this. So one circuit you can be given may look like this. that. Like that. Okay, so let's give some values now. 2 microfarads. So this is the capacitance of this is 2 microfarads or microfarads. 4 microfarads. 9 microfarads and 3 microfarads. Yep. And then the power supply, the voltage, let's say it's 6 volts. Negative, positive. So the typical questions that you can be asked are this. Find the equivalent capacitance. Find the total charge in the circuit. And the other question may be find the charge on each capacitor. All right. Okay. So the first step is to reduce a circuit so we can find the equivalent capacitance. So basically, reduce all those 4 capacitors into 1. Well, let's see. These capacitors here are in parallel. And also these 2 are in parallel. We join parallel capacitors by adding them. So your 9 and 3 basically combine into a 12 microfarad or faradio. And your 4 and 2 into 6. You have a 6 and a 12. And as you can see, they both are now in series. So to find the equivalent capacitance, we have to combine in series 6 and 12. Well, we use the equation for capacitors in series. One over C equivalent is equal to 1 over 6 plus 1 over 12. Right? Okay, so 1 over C equivalent is common denominator 2 over 12 plus 1 over 12. Now I can add this 3 over 12. But wait a second. That's 1 over C equivalent. So I flip it. C equivalent is 12 over 3, 4 microfarads or farads. That's my answer for A. Very easy. Now I can also find the charge. Here, the charge is the equivalent capacitance times the voltage supply. The total charge is the equivalent times the voltage supply, which is 6. So that will be 4 microfarads multiplied by 6 volts. All right. If you multiply a microfarad times 1 volt, the answer will give you, the answer will be microcoulombs. 4 times 6, 24 microcoulomb. And that's the answer for B. You see, very easy to find the equivalent capacitance and to find the charge on the circuit. Those two questions should actually be pretty straightforward. What you need to be careful though is how you find the charge on each capacitor. You basically have to go back, bring this back here, and split the charge, which you know in parallel is not constant. But let's go backwards though. All right. Let's do part C. For part C, you first need to notice, if you go backwards, that 6 and 12 are in series. So by the theory, you know that the charge on 6 is equal to the charge on 12 equals to 24 because they are in series. So you start with that statement. The charge on 6 is equal to the charge on 12, which is equal to 24 microcoulomb. So if that's the case, then you can use that to split the charge among 4 and 2 and 9 and 3. Let's start with 4 and 2. 4 and 2 are in parallel. Whenever you have capacitors in parallel, the voltage is the same. So like this, now you say that the voltage on 4 is equal to the voltage on 2. And what's the voltage on 4 and on 2? Is the voltage on 6. And what's the voltage on 6? Well, we need to remember our equation, right? So you may want to have this always. C equals to Q divided by V. Now, since I want voltage, voltage is equal to Q divided by C. So Q is 24 microcoulombs. And C is 6 microfarad. 24 divided by 6, 4 volts. So that means that the voltage on 4 is equal to 4 volts. By that equation here, the charge is equal to C times V. 4 times 4. Therefore, the charge on 4 is 16 microcoulombs. Similarly, the voltage on 2 is 4 volts. Then the charge on 2 is equal to 8 microcoulombs. How do I know that's correct? Because 16 plus 8 is 24 microcoulombs. All right. So I split the charge between among 4 and 2. All right. Now let's do 9 and 3. For 9 and 3, the analysis is the same. The voltage on 9 is equal to the voltage on 3 is equal to the voltage on 12. The voltage on 12 will be 24 divided by 12, which is 2 volts. How do I know that's correct? Because 2 plus 4 is 6. Conservation of energy. So we can just say here that the voltage on 9 is equal to the voltage on 3 is equal to 2 volts. If I have the voltage, just like I did here, the charge on 9 will be 9, the voltage, 2 times the capacitance 9 times 2, 18 microcoulombs. And by conservation of charge, 24 minus 18, 6 microcoulombs. Or you can just do 3 times 2. So the charge on 3 is 3 times 2, 6 microcoulombs. There you are. That's how you solve.
Wait, Professor, could you explain how you get 2 volt? Could you?
By dividing 24 by 12.
Oh, okay, got it.
All right. By dividing the total charge by the capacitance 12, which is the equivalent between 9 and 3, or the combination of 9 and 3. All right. Are there any questions about this or any other questions? So remember, that's just one example. There are different setups. I just did one of them. I want to do another one where we might have to do a different procedure, especially towards the end. All right. Keep in mind how I organize this, right? I try not to skip any of the steps. So all the steps are in there. And of course, the main difference between what you do in the web assign with what we do in class or even on quizzes is the numbers, right? I mean, I try to give you easy numbers, so look at those nice answers. Cengage, they give you very annoying numbers sometimes, but the procedure is the same. And I believe there is a problem like that in the assignment anyway. Well, let's do another one. All right. Let's do another one. All right. All right. So another type of setup that you can have also in circuits with resistors is like this. Two capacitors like this. Another one like this. Like that. All right, let's give some numbers now. 3 microfarads. Let's give 4 here. 12. 6. And 2. Get some fractions in there. And let's 12 volts. All right. So the first question for this again. Find the equivalent capacitance. Find the total charge. And now you're gonna find the charge on each, but also the voltage on each. I mean, you just saw over there that the voltage is that you can also split the voltage. So let's do that here. All right. All right. I'm doing this example because this is a good way to address a misconception that may happen in the assignment, on an exam, or a quiz. Be careful when you try and do this. And this. If you try to say that these are in parallel and these are in parallel, before realizing that these are in series, then you will get the wrong answer. And I've seen this a few times, it happens. So be careful. That's not correct. The main connection is first the series connection between 4 and 12 and between 6 and 2. So I'm going to combine in series these two. And then in series, I'm going to combine these two. Once you combine these two in series, you can then do the parallel connection between the combination of these two and these two. All right. So that's where you have to be careful. Once you realize that, then you are set to start this problem. 4 and 12, I'm going to write here 1 over C is in series, right? So we have to use that 1 over is equal to 1 over 4 plus 1 over 12. The common denominator is 12 times 3 times 3. 3 over 12 plus 1 over 12. That's 4 over 12. So 1 over C is 4 over 12. Therefore, C is equal to 3 microfarads. That's the combination of this. So let's write it here. That's the combination. All right. Now I'm going to do these two. 6 and 2. Let's call it 1.
Is the professor lagging for anybody?
Yeah, for me.
Yeah, bro.
Sorry, I think I had a connection issue. Let me see if the recording is still going on. Yeah. Okay. So what I was saying was the answer for part A will be combining 3 over 3.5. That will give you 4.5 microfarads. All right, that's part A. Now I can also do part B. Part B is asking me to find the charge on this circuit. Well, we have to write for part B, the charge is equal to C times V. So here will be 4.5 microfarad multiplied by the voltage 12. And that will give you around 54 microcoulomb. A and B. All right. So you found the charge on the circuit, Q total, and you found the equivalent capacitance, of course. All right. Now we have to do the charge on each and the voltage on each. The thing about splitting the charge and the voltage, you can basically do both at the same time. Let's see. So that charge is going to be split. Why? Because 3 and 3.5 are in parallel. You see? But let's take into advantage what we know about voltage. Since 3 and 3.5 are in parallel, then they have the same voltage. So let's forget about this for now. Let's focus on this. The voltage on 3 is 12 volts. So if I have the voltage on 3 and the capacitance, which is 3, I can find the charge on 3. And if I find the charge on 3, I know the charge on 12 and the charge on 4. The charge on 12 and the charge on 4 is the same. And the same to what? The same as 3. So I might have to write this in here so you have this as study or to review. First of all, the voltage on 3 is equal to the voltage on 1.5, which is 12 volts. And you may want to write there because they're in parallel. And then also the charge on 3 is equal to the charge on 4, which is equal to the charge on 12. All right. Now, from this first premise, if the voltage on 3 is 12, then the charge on 3 will be the capacitance 3 times the voltage 12. Well, 3 microfarads times 12, that's 36 microcoulombs. Perfect. That means I have the charge on 4 and the charge on 12. So I found the charge on 4 and 12. So you may want to go back to the diagram and write that the charge here is 36 microcoulombs. If the charge is 36, you can find the voltage on 4 and the voltage on 12. This is equal to 36 microcoulomb. Then the voltage on free is the charge divided by the capacitance. And what's that? 12 volts. Oh, wait. Something wrong here. Divided by 4. The voltage on 4. I already found 3, right? So why do I need that? This. So that's 9 volts. That's on 4. And what about 12? Well, think about it. Let's use some physics. The voltage is 12. 4 is already getting 9 volts. So the voltage on 12 is 12 minus 9, 3 volts. And there you are. I split the charge and I split the voltage. Sort of at the same time, you have to use both to kind of make sense of that question, right? Are there any questions? I'm gonna do 6 and 2 now, but I wanna make sure that that's clear. As I said, you wanna write that the voltage on 3 and the voltage on 1.5 both are 12 volts because they are in parallel. And then you wanna write that the charge on 3 is the same as the charge on 4 and the charge on 12 because they are in series. And then you can split the charge, and then using that you can split the voltage. All right.
Wait, so Professor, the 36 microcoulombs, is that for Q3 or Q4?
For both. They both have the same charge.
Okay, so Q3 equals Q4, which equals
Equals to
Q12, which equals 36 microcoulombs.
Yeah.
Okay, so it's really just a voltage that's not
Yeah,
constant.
yes, the voltage is split because in series the charge is constant.
Okay.
All right.
Wait, Professor, so Q3 and V3 is a combination of the top one, right?
Yeah.
Okay.
Yeah. We're just doing the. We're gonna do the 6 and 2 now. Okay, for the 6 and 2, you know what's the charge between 6 and 2. If the charge here is 36 and the overall charge is 54 there, right? Like the charge on the circuit is 54 and the charge here is 36. You know what the charge that is going through 6 and 2. By conservation of charge, 54 minus 36 is 18. That's the charge here. All right. So that's what you write. Let's write here Q is 18 microcoulombs. 54 minus 36. And then I just do the procedure. Let's erase this. So the charge on 6 is equal to the charge on 2, which is equal to the charge on 3 halves, which is 1.5. And what's that? 18 microcoulombs. So you basically split the charge already, if you think about it. You already found the Q on each. What about the voltage on 6? Well, the voltage on 6 will be the charge on 6, which is 18, divided by the capacitance. And what's that? 3 volts. Well, the voltage on 2, you can just say is equal to the voltage given minus 3 volts. And that's how you split the voltages. All right. Any questions? Nothing? So remember, we've done 2 different examples. I'm gonna do one more just to reinforce we have time before we basically finish with this chapter. All right. The main idea or the main thing that you guys have to keep in mind is you just have to be organized. If you are organized and if you understand what series and parallel mean, then you are going to be more than fine. All right. And remember how we always keep using the equation C equals to Q divided by V, or its variances, right? Q equals to CV or V equals to Q over C. We use that equation. That's the key equation that we have to use to understand this. All right. It's built from that. All right. Let me just take a look and see what a good example of this. Oh, wait. Yeah, this one. Okay, let's do another one. Okay. So one last example of this will be a circuit that looks like this. The battery here, a capacitor here, and then you have a junction sort of here. Why? Because you have a cable going here, and then another cable, wire, and then you have this connection. All right. 6, 3, and 2. Yeah, you know what? Let's give you something with fractions because might as well, so you know how to work with that. Yep, it's a good idea. And let's give you here 10 volts. The book won't give you nice numbers, so might as well give you one example like that. So let's find the equivalent capacitance. And let's find the charge on each. All right. In fact, you could see a problem like this in a final exam, maybe. Not the 2 questions, but maybe just finding the charge on one of them or find the equivalent capacitance. All right, so here maybe it's a bit easier to realize that 6 and 3 are in parallel first, right? Because of this junction. A junction or a node is an intersection of 3 or more wires. All right, that's going to be very important when we start doing more complicated circuits, especially with resistors. All right. So basically, if you think about it, you have charge / current, and then it splits here and here, and then goes all the way here, and then all here, and then it combines again. Anyway, 6 and 3 are in parallel. So we combine these two. Into 9 microfarads. All right. But this one here and this one here, the combination of these two and this are in series. Therefore, we have to find the equivalent capacitance in series 1/C³ equals to 1/2 plus 1/9. Oh. Well, the common denominator is 18. So 9/18 plus 2/18, that gives you 18/11 microfarads. I mean, if you split it, of course, because this is right. So you split it and you get that. Okay, so I found this. Now, how do I find that charge on each? Well, the problem is not asking you this, but we need to find that charge on the circuit. So I found the equivalent capacitance. Let's find the charge on the circuit. The charge is the equivalent times the voltage supplied there. And that will be 180/11 microcoulombs. Okay, let's approximate there. That should be around 15, 16. 16.4. There is approximately 16.4 microcoulombs. So that's my my charge. That's the charge on the circuit. Now, if we go back to this circuit, the charge is split here. But look, it's a split and then it's combined here. So I already know what's the charge on 2. The charge on 2 is the net charge of the circuit, which is 16.4. So the charge on 2 is 16.4 microcoulomb. Now I just need to split the charge between 6 and 3. All right. Okay. So the voltage on 6 is the same as the voltage on 3 because of parallel. And what's the combination of these two? 9, which is the voltage on 9. And the charge on 6 will be the voltage on 6 times the capacitance 6 microfarads. That's going to be Q. But what's the voltage on 6? What's the voltage on 9? Well, the voltage on 9 is the charge on 9, which is this, right? These two the voltage of 9, like what the voltage of 9. The voltage of 9, yeah, will be the charge divided by the voltage of the combination. All right. Since these two are in series, the charge on 9 is this. Q divided by C. And that's approximately not 2, it's 1.5, I believe. 1.8. 1.8 volts. So that's the voltage on 9. Which is the voltage on 6? So what's the charge on 6? 1.8 volts multiplied by 6 microfarads. That will be 10.8 microfarads. All right. You can find the charge on 3 by using the same the voltage on 3 is that. Six times 1.8 is, sorry, times 3. 1.8 times 3 is 5.4. 5.4 microcoulombs.
Wait, Professor, that doesn't add up to 16.4.
That's because of the approximation, because of this.
Okay.
That is approximately 16.36. I rounded to 16.4. And this actually gives you 1.8, 1.82. So that's why. So I'm rounding these numbers. But even when you add them, you get 16.2, so approximately. Right. Remember, these numbers are all because of this. That's an irrational number. All right. Or sorry, that's an infinite rational number, like has infinite decimals. So, but that's how you split the charge, the voltage, and the circuit given there. All right. So there you are. You should have, or you have now all you need to complete assignments 2 and 3. All right. 4 and 5 deal with the next chapter or chapters 17 and 18, which is current, resistors, Ohm's law, and circuits in parallel and series of resistors. All right. So does anybody have any questions?
So Professor, so the test will be covering from 1 to assignment 1 to 5, right?
Yeah. Assignment 5 is
Resistor in series and
Yeah.
parallel. It won't cover assignment 6, would it?
If assignment 6 is RC circuits, no, RC normally I put it aside for the final. No, only
Okay.
assignment 1 to 5. Yeah.
Okay.
So you guys should like start doing assignment 2 for sure. 2 and 3, in fact. Not just for this week's quiz, but for the exam, which based on the pace, I'm gonna say, guys, test number 1, you wanna write this in your calendar, is gonna be Tuesday the 18th. All right. Tuesday the 18th in person, we'll have test number 1. The advantage of that is that you guys can stay as much as you need. I don't have any class after that. And the lab before that is actually easy. So you're probably gonna be done with the lab way before we have, so you have time for that. Okay, so Tuesday the 18th, with the last topic being circuits of resistors, probably Kirchhoff laws, we'll see.
Are you able to like hold like review section after the lab to like go over like questions that might be
Only if
on
we
it?
finish the lab early.
Okay.
And I guess, I mean, if you are done with the lab, yes. I mean, because normally the way the lab works is that after the first half, the students are working independently. So yeah, like you can always ask us. And the thing is that the labs are matching what we're doing in the class. So in some way or form, by doing the lab, you are kind of studying for studying the material, right? But yes, you can ask questions when you're in the lab for sure. Before, of course.
Is there gonna be a study guide you're gonna release?
There is a study guide. There's a video study guide that you can watch in modules.
Okay.
And there's also one in the modules, I believe. Okay.
Okay, thank you.
Where is this? I'm gonna take the time to double check the attendance. Just give me a couple of minutes. Okay, who is this student? So I don't have them in the list. Alistair Julian. I don't have you in the list. So I don't know how you got this.
That's me, Maxima. I'm just using a different.
Okay.
Yeah.
All right. So there's still some students. All right. So let's use the chapter slides for a bit. The video was referring to, by the way, is here. So today's class has been recorded or is being recorded. I'm gonna publish it in discussions today. And there's another one here that you can watch, it's probably like very similar. And the review for exam 1 is here. So there you are, okay? Just as I always said, even during the normal semester, and there's a study guide here. Make sure that you really give yourself time to go over the material. All right. The assignments are your best bet, but if there's something that wasn't clear from the class, you can always go back to it, right? Now, I feel like it makes more sense to do it when we're online, because online, there are things that you can miss. In person, I mean, I believe that it's a bit easier to catch on the concepts. But there you are. It's actually.
Professor, for the first test, how many questions do you think it'll be on it?
No more than 7.
No more than 7. And then timing wise, you said we can go, what's like,
So
yeah,
it's the
how
whole
long?
class. It's the whole class. But since I don't have a class after, you don't really have the pressure to finish because I have to leave.
Okay. All right, thank you.
No, the exam is all short-ended. Short answer questions. All right.
The question for the exam is going to be straightforward, right? It's going to be like question that we did in class. Or,
Yeah. Like for example, you see these questions that we've been doing today, part 1, part 2, like that.
Okay, so it's not going to throw us like curveballs where it's just going to have to like substitute the equation out of the equation to find something else, right?
What do you mean? Like it's all going to be based on what we've done.
Okay, got it.
Okay. So
The exam is going to be similar to the in-class examples or more to the homework?
no, more to the, I would say in-class examples. That's sometimes what, but if you think about it, right, especially now when we're doing circuits, a lot of the examples I'm doing in class are very similar to the ones in the assignment. The main difference is the way the question is worded maybe, and the numbers. But okay, let's take some time to show you. If you take a look at the assignment, yeah, I'm sharing my screen. This is a question that you are getting in the assignment. We just did that question. Look at this. Look at this. So it's the same. It's just the way the question is, or look at this, right? We did that last class. So it's just how the question is worded. The web assignment normally goes a little bit and beyond because you have time to do this. Like you are at home, you have the book. You can go back to it. You can read the question. In an exam, the numbers are easier and the questions are more to the point because it's an exam. But the questions are very similar to, or for example, look at this question we did today, right? So whatever we do in class is based on questions from WebAssign or similar, all right?
Well, what about electrostatic? Would the question be as difficult as the electrostatic one?
Electrostatics is normally difficult regardless.
Okay.
Because it's, I mean, it doesn't matter if it's on summer or on a regular semester. Electrostatics is difficult because what makes electrostatics a bit difficult is the fact that you have to deal with vectors. And you have to deal with some numbers that are like kind of complicated. If you go over that, like if you practice enough problems, like, you know, when you have components, directions, it becomes easier, all right?
So
Circuits is easier because the numbers are easier and the concept is actually, some of you have seen circuits before in physical science school.
So Professor, if we understand how to do the electrostatic question on like homework, we're basically set.
Yeah, so then that will get you ready for the exam.
Okay.
But remember, in the exam, there is no textbook. There is no help, right? You only have your equation sheet. So I normally tell students try to practice or try to do at least one of the equations of the assignment without any help. Because I can see many of you probably doing the assignments with an open book, which, I mean, it's okay. But try to see or try to test your understanding without using any sort of any external help. Without Google, without looking at the textbook or the notes. That will give you a good measurement of how much you have retained. Okay. But anyway, you have a week. And during the week, we are going to have questions, so you guys can always ask if there is something that is not clear. All right. All right. So chapter 17 and then chapter 18 are going to deal with the introduction to electric current, Ohm's law, which is the lab of tomorrow. So that's good because we're doing this tomorrow. Electric circuits, and then this. This one we already did, so don't worry about it. This one you are learning in the lab. So we're going to talk a little bit about this. RC circuits is important, but that's not going to be in the exam. So basically, these are the last topics before exam number 1. Now, Thursday quiz won't have any of this. I already have the quiz here. So the quiz for Thursday has 3 questions with 1 extra credit, and they are all based on chapter 16. All right. So that's what I'm saying. You need to start doing the assignments 2 and 3. And then that will give you 100 on this quiz.
Professor, how many quiz are there in this class?
Probably 5, because I'm gonna throw you guys a few online.
And is there going to be any pop quiz? Because on the
No, I don't do that. Not even in school I do that.
because on the syllabus it does say pop quiz.
No. With at least I don't know. That's that general syllabus is the syllabus that we use for all the class. So some professors may do that. So that's why it's there. That's why
Okay.
it's there. Even for labs, sometimes they do that. But no, I don't like to do that because there's not really time to do that on summer. That's why I'm doing the quizzes online, or most of the quizzes online. Okay, I want to make sure that we go over the material that you need to learn. By the way, guys, the quiz on Thursday, that will be time. You will start at 2. You cannot go beyond the class time. Okay, the quiz on Thursday will start approximately at 2, and you have the rest of the class. So please make sure you have your calculator, your equation sheet. I don't want you guys to be wasting time on that. All right. Anyway.
Will this section be recorded or will it not?
Yeah, it's all being recorded right now.
Oh.
Yeah. Okay, so the questions are from chapter 16. So up until what we just did. What is electric current, guys? So up until now, we've been talking about static charges, right? Electrons, protons, maybe moving due to an electric field, but we've been having charged objects that are basically in a fixed position, and we've been exploring the electric potential energy, and in chapter 15, we went over electric force, electrostatic force, attraction, repulsion. So the idea with electric current is to explore situations like this. So what you're seeing there is a circuit where you have a light bulb connected by a series of wires to another light bulb, and then you have a battery. Now, I have already introduced the idea of the positive and negative terminal of a battery. In the first lab, you guys have seen that you can plug a power supply using banana or alligator cables, and you can use that to power a small circuit. In this week, you're going to be using a light bulb and a resistor, and you're going to connect it using a switch and a battery to close a circuit to analyze what we know as Ohm's law. Ohm's law is basically the relationship between current, voltage, and resistance. What do you think is resistance? In mechanics, you went over the idea of friction. If you have a mass and there is friction and you exert a force, eventually because of friction, the mass will slow down because of the force of friction. The idea with resistance, right, is to have some sort of resistance, yeah, to the flow of current. So if you have a cable, a copper cable, and you introduce resistance or you place resistors in a circuit, you can calibrate, you can slow down the motion of the electrons. You can basically reduce the amount of current by adding more resistance. That should give you an idea of the relationship between voltage, which by the way, voltage is now what we call electric potential, the voltage of a battery, volts. Resistance, which we measure it in ohms, and current, which is our new definition today, which is given there. Current or electric current is defined as the amount of charge flowing in a given wire or circuit by the amount of time. Is the rate of change of current per unit time. Delta Q over delta T. Coulombs per second. That is the ampere. All right. So, to analyze, to introduce current, we first have to introduce the idea of a battery. Now, electric potential introduced the idea of volts. And then we use that to define the electric potential energy. So let's use that to analyze what a battery is. Basically, a battery, by using chemical reactions, will provide a potential difference between the terminals. 1.5 volts, 3 volts, 6 volts. It depends on the size of the battery. The higher the battery, the more charge it can hold. Right? Q equals to CV. So we still use that equation. But now we're going to forget about charge. We're going to focus on the voltage. If you have a battery with certain voltage, you are basically introducing electric energy in the circuit, which allows current to flow. It's like what you see in the picture there. If you have some sort of potential difference between the initial position where you are serving water to position B here, there is a potential difference, right? Because of the slope. So the current can flow just like water. That's why in some textbooks, they use the analogy of water flow to current flow. And that's going to be useful when we start talking about junctions, nodes, right? Here, you are seeing the you are seeing how we can define a circuit. You have the battery here, you have the switch, or how we label it, and you have here the light bulb, which might be your resistance, which we label it with R. The battery, normally we label it with V. Normally, not always. Why? Because in the next few slides, you're gonna see that we're gonna introduce the concept of E. What is this E? Well, in theory, that's the nominal value of a battery. When you buy a battery in Radio Shack, I mean, Amazon, Radio Shack, I don't think it exists anymore, unfortunately. But when you used to buy batteries in stores like Radio Shack, right? They will give you the value of the battery, right? 1.5, 9 volts, maybe, depending on the size, depending on what you need it. But that's the theoretical value of the battery. If you use a voltmeter, especially if the battery is connected into a circuit, like here, you may read 8.8 volts, not really 9 volts. So where did the 0.2 volts went? Well, that's when we introduced the idea of electromotive force. When the battery is disconnected from any circuit, we can say that between the terminals, we are measuring the EMF. The EMF is basically the amount of voltage required to move a charge from point A to point B. In other words, is related to the work done to move a charge from one potential to another potential. That should sound familiar because that was our definition of electric potential. Basically, the amount of work per unit charge. But as if the battery is unplugged. When you plug the battery into a circuit, you obtain the voltage. So what is a relationship? Well, it's not in the slides. It might be in the textbook. But the relationship between EMF and voltage is this. V equals to the EMF minus IR. All right. The reason they don't give you that equation there yet is because the IR is what we are going to define as Ohm's law. And let's go ahead a little bit. This R, if I were to draw a battery, in real life, a battery is not like this, right? It's a device. I mean, you have seen power supplies in the lab. Those big green thingies. A power supply or a battery, they have inside an internal resistance R. The internal resistance is the reason why the voltage is different than the theoretical value or the EMF. Now, depending on the specification of the power supply or the battery, normally the value of little r is very small, so small that it can be negligible. That's why I said, if a battery is of 9 volts and use a voltmeter and you read 8.8 volts, the 0.2 volts or 8.9 volts, that is because of this. But that's still very small. And there are some cases where the readings may be 8.95, 8.96 volts. So the difference is basically negligible, right? But that's the reason why you have, a difference between the voltage and the EMF. And I'm pointing this out because when we do electromagnetism or magnetic fields and induction, we're gonna go back to the idea of an EMF, all right? But for now, we're just gonna keep it as the voltage V. Okay, so that's to introduce a few new variables, the current I, the resistance R, and the value of E. Now let's talk about direction of current. You are gonna notice that when I draw the current direction in problems, I'm going to use the green direction that you see over there. So from positive to negative. However, you probably already know that there is a problem with that. When the idea of current was introduced and discovered, it was believed that the current was due to the motion of positive carriers, aka protons. However, after we have been deciphering the atom, after understanding the composition of the atom, more specifically the nucleus of the atom, and realizing that protons are heavier than electrons. And as I explained the first day of class, you actually have transfer of electrons, right? Then we realize that current is due to the flow of electrons. So it doesn't make sense that electrons will leave the positive plate or the positive terminal of a battery, right? It makes more sense that current is actually on the red direction. However, the convention was built based on the green direction. So we just use that. Does that mean that we are wrong and everything we've done so far in science is wrong? No. You're gonna see maybe even tomorrow that especially digital ammeters, they read negative currents. So what's the meaning of a negative current? Well, basically means that you are reading current in the opposite direction. The value of the current is correct. You just have to change the direction of the wires. We call that in the lab changing the polarity of the cables. So there is not really a problem in terms of the value of the current. It's just a direction of it. Do we have to be careful? Sometimes in electrical engineering, you have to be careful with that, yes. But in basic circuitry, not really. You can just change the poles when you are plugging into the ammeter or the battery, and that fixes the problem, which is why we can just keep the convention for the direction of current. All right, so that is with the direction. And then let's talk about what's really happening when current is flowing in a cable. Whenever you have current flowing in a conductor, right? What we actually see is there in front of you. We don't see electrons flowing straight without any sort of bouncing, because there are so many electrons flowing per unit volume in a cable. And many of the cables that we see in real life are so thin, right? That electrons are gonna bounce randomly. So the motion of electrons, because of these collisions or bouncing, is actually very small, or sorry, very slow. So electrons can take a very long time. And we're gonna do a problem tomorrow at the beginning of class for sure, because that's a long problem, to show you how long it takes for an electron to travel in a high power cable. You know those cables that we have outside that we use to provide electricity in cities, right? High transmission cables. They have large amounts of current. Therefore, they should have a large amount of charge flowing in them. But because there is so much charge, there are so many electrons that they're gonna bounce so much that it can take years for an electron, for a single electron to travel from one end to another. So then how come electric signal travels so quickly? Because electric signal is governed by the electric field. When I introduced the idea of an electric field, I said that as soon as you create, let's use that word. As long as you have an electric potential between a parallel plate, you have an electric field in between the plates. It's the same with an electric signal. The electric signal is governed by the electric field. That's why the electric signal travels much more quickly. All right. Okay, so let's actually show you the equation for this. So what is the equation for electric current? That's basically the microscopic definition of current. So if you have a cable, I'm going to zoom in like in the textbook. And you have a surface area which can be approximated to a circle. Area A, some distance delta X. So that multiplied gives you the volume. And then we have the electrons or the carriers moving from left to right. The electrons move very slowly with what we know as a drift velocity. So these electrons here are moving with this VV, drift velocity. Now, the amount of current depends on the density of carriers. Is the amount of carriers per unit volume. Now, that depends on the type of cable. Aluminum, gold, copper, they all have different densities and different molar masses. So you can use both to find the density of carriers. So then we can define the current flowing as the density of carriers N multiplied by the drift velocity multiplied by the area multiplied by the charge of the electron, the magnitude of it. This is the microscopic definition of current. Where this N is the density of carriers. This is the drift velocity, A is the area, and that's the charge. So there you are, okay? When we need this equation tomorrow to do a very similar problem that is in the textbook, and it will show you how slowly electrons move. So is that the only definition of current? Not really. The more simple definition is when we start using the idea of conductivity or resistivity, basically bringing Ohm's law into the mix. All right. So let's share this again. So what is Ohm's law? Ohm's law is not really a universal law. Why? Because a lot of materials are what we know as non-ohmic materials. They don't follow Ohm's law. Tomorrow, before class, we're gonna be given two different materials, a resistor and a light bulb. A resistor, which is ohmic, you will find that it will follow this. If you plot the voltage supply to the resistor as a function of current in amperes, and this is voltage in volts. If you plot these two in the X and Y axis for an ohmic material, you're gonna find this. So what do we see here? We see a linear trend. You see this? As the voltage increases, the current increases. That means that the rate of change is constant. And what is the rate of change? That is your value of R. And what's R? That's the resistance. The resistance is defined as the change of voltage, or V, divided by So V over I. That's Ohm's law. Right here, R equals to V over I. Voltage over ampere, that will give you the units of ohms. So 1 R, the units are in, let's put it here, the units of R are in ohms, which are equivalent to the horseshoe, like that. That's Ohm's law. That's what you will find. So what about a non-ohmic material? A material that doesn't follow Ohm's law. What you will see, for example, with a carbon resistor or a light bulb, is this. So if you were to plot let's suppose you have a non-ohmic device, resistor. If you were to plot V versus I, you will start seeing something that looks like Ohm's law, but then you start seeing this. Right? So it's not really linear. It's more like a power sort of relationship. So it's not linear. So that doesn't follow. So that's why it's not really a law. It's not really a universal law. It's convenient only for certain devices. All right. So that's Ohm's law, and that's a microscopic definition of current. We're going to use those two to introduce resistivity, and then to do some examples on how we use current with different materials, and then we can introduce circuits using resistors in series and parallel. All of that we will be doing. It will be done tomorrow. So I'm going to stop the recording. I'm going to double check the attendance, and please, if you have any questions, let me know while I'm double checking this. Remember to start working on assignments 2 and 3. All right. I know they are due next week, but that will be the best way to start mastering the previous concepts. All right.